Starting. And the Hangout on air is live. Thank you, everybody, for checking in this special edition. Really apologize for the technical difficulties, but we are live right now. And I hope the health of the stream is good. I am currently joined by the Mind of God and George Hnatiuk. They will be discussing water test, I called it. So, gentlemen, go ahead, carry on, and the floor is yours. I'll mute myself.
Okay, Jose, I'll just do a brief preamble just because we're starting a new stream, just why we're here. So George and I have just decided to talk, talk about tests, lay some foundations, get some feedback from one another. Nothing quarrelsome. We're just bouncing ideas back and forth. I prepared a PowerPoint to sort of guide the dialogue. It's not going to be WWF kind of thing. We're just gonna, talk and share ideas. And the idea was come up with tests with off-the-shelf parts. So it has to be sort of tangible, touch and feel. And, it could be very, very expensive. We didn't put a dollar limit, and it could be, doesn't have to be time bound either. So those are the sort of parameters. And we're trying to sort of bring this debate sort of down to earth. And in particular for those who are sort of engineering scientifically inclined. So I'm going to share my PowerPoint. So if you guys can just let me know in the chat that you can see my screen in a second, that will help. And if you can let me know the audio is good too. So if you guys can let me know in the chat that you can hear me and my title slide is visible, I'll get going.
I'm presenting you. We'll wait for some feedback from the chat.
Okay, I can actually see it now. It looks good. Okay. All right, good. So I call my talk Earthshape, Thoughts, Tests, and Teammates, and I'll explain, the motivation behind that title. Just as my background, I'm a BSc in EE. I have a master's in EE, but I work as a CPA now. So George is very much more hands-on and doing this stuff sort of day to day. But I think just with him and I, and especially I would feel both of our ability to kind of explain and grasp concepts. We can speak a similar language, though he's obviously much more into the details. But I'm going to use some engineering analogies that may help people. So this is sort of the structure of the talk. It's going to be mostly conceptual. I'm going to try and not bore people, just sort of do things, at this point from a high level. But if anybody wants to engage me on any of these points going forward, either in Jose's channel or wherever, I'm open for sure. These are just my initial ideas on sort of avenues that we can go down to, look at different tests that have already been happening for this flat Earth, ball Earth debate. So I'm going to go through my initial thoughts. I'm going to go through what I feel is the foundation to almost everything that I've thought of to this point is developing a neutral and local coordinate system, and I'll explain what that means. Then I'll go into 3 tests, concepts at least. First one's multiple drones using a daisy chain of and lasers, doing wide angle lenses. I'm going to talk about more of a sort of qualitative observational type thing that we could do. And then George and I have some thoughts, feedback. Mine is sort of an addendum to Sly Sparkane's water level tests, and I'll just spend a couple slides on that. And then I'll talk about where I see this sort of debate happening just sort of organically, and it's inevitable. And I'll put my thoughts out there on that. So starting with my initial thoughts, George, you can jump in anytime, man. We'll just keep it informal. If there's something you want to chime in on. But so I want to start this thing with an analogy in electrical engineering. If it's not actually new, but this concept of multiple antennas at the transmit and receive is something that has been explored for a while now, and really allowing an expansion in the capacity and increased data rates. And so I want to use this analogy to this test, this ball Earth, flat Earth testing. So imagine if you have a bag of ones and zeros. Let's say it's our responsibility to transmit those ones and zeros using these multiple transmitters through a channel, which is statistical, time varying. And then you have M receive antennas at your disposal. And then our job is to assimilate that data and then, get the bag back exactly the way it was sent. So the cool thing about this from an information theoretic point of view is that when you transmit information and you have the luxury of transmitting across multiple antennas, you could either send the same signal across all the antennas and then propagate that, and then all the receivers are sort of anticipating the same signal, and so they can take advantage and essentially they can add out or average out noise and effectively increase the signal to noise ratio. So you get what's called as like a diversity gain, because you're sending the same signal across statistically independent channels, and then you can have a better estimate of the sent value at the receiver through diversity gain. And then another option is you can actually send independent data streams across these transmit antennas, and then you can increase the capacity that way. And so that's what's known as multiplexing gain, where you basically treat each one of the transmit and receive antennas as an ordered pair, and then you can get what's called multiplexing gain. So in different scenarios of what the channel is doing, you can increase the reliability of the received signal and then be able to decipher what it is. So I'm going to draw analogies to that in terms of these tests for flat Earth and ball Earth, is that this trade-off is essentially really what's going to start happening when people start doing different tests, and then in some cases the same tests in different locations, that you can have what's known as a diversity gain on tests, where you do the same test, but you do it over and over again, potentially in the same location, or you can do it in different locations, and then effectively the error will get averaged out. And then in a good way, the more the test is sort of broadcast and done, we can get more and more confidence in the result. And so another option is you can multiplex, you can do a variety of tests. In this case, you could be susceptible to higher errors, but if you do a lot of independent tests, and even if the errors are higher than in the diversity case, you can still make an inference on the shape of the Earth. And so both fundamentally are statistical and multivariable in nature. So we have to be careful, because one test may say that the Earth is curved, but the curve may not be precisely what is known already or be measurable. And then even if the Earth is deemed to be flat or appears flat, there could still be a slight curve. So to me, it's very, very important to invoke a diversity of tests and a multiplexing tests, which are independent tests, to get to the solution in a rigorous way. So that's sort of my preamble, the sort of way that I see this conceptually, just in terms of the number of tests that have happened in the past. And I think more and more people are getting careful about what they label as proof and what they label as just evidence. And so I think that's already sort of understood on both sides. But to me, as a double E, those are kind of the way I think about it. That's the analogy that I think of in my head. So the first thing that I want to go through, and I think is going to be the most important thing over time, that will help us do this without the help of the military or the government or NASA, is we need a neutral local coordinate system. And I'll explain how this is my first my sort of proposal to kind of get the ball rolling on this, if it hasn't already. So just from a sort of high level, the way I see this happening is that the one cool thing about GPS is that it's so available now because of our phones. And so what I would propose, at least conceptually, is that you can use GPS, which is a position in three-dimensional space. It gives us a latitude, longitude, and elevation. Anybody who has the Compass app on their iPhone, if you're an iPhone user, can pull that up. And, you can get a sense of where you are, in the world. And so I've played around with my iPhone app a little bit. I got a sense of what the elevation was at my golf course, because has really good views of the city and stuff. And so the way I see this happening is that we exploit the fact that GPS is fairly ubiquitous and hands-on and available to us, and that if you can position, and I'm not recommending anybody or giving homework to people, but I'm just saying this could be something that we could outsource or do if we have enough space and time and resources. But essentially, if you can draw a grid using lasers, which will invoke a straight line, at least at the local level, and then use the GPS coordinates, which will presumably vary at these different locations, and create sort of a rectangular grid, straight line grid this way. And so to me, the nice thing about this is that you're creating it on a local level. You're using off the shelf parts, and then you're less susceptible to ambiguity, just because this is very, very reproducible. Like you could go and reproduce this grid regularly. And so the distance between those iPhones would be sort of the granularity of the grid, because there's obviously errors involved here, because, you know, you can't sample every, you know, few inches, obviously, with this type of technology. And so, but those, at least coming up with those grid points, to me serves as a very, very powerful foundation. And then from that, what I would propose is that, given that fixed set, you know, let's say it's done over even just like a, you know, 500 meters by 500 meter grid. And then what we can do is then use the GPS coordinates to extrapolate out. And so right now I'm dealing as if it's in 2D, like on the surface of the Earth. But ideally, if this could be raised up and sort of take the actual physical curvature of the Earth out of play, if it exists. But the idea is fundamentally to get these GPS coordinates lined up along straight lines governed by lasers, and then extrapolate out, and then confirm that our extrapolation is correct. And then that serves as a foundation for a grid that we can use to do other tests. And so this is essentially overloading, or sort of piggybacking off of GPS, which is existing, to create sort of a regularized, neutral, and local coordinate system that is just straight lines. So this to me is the foundation. And so I'm going to now propose what I think will be sort of the major game changer. Like, it looks like the cameras and the high res P900 and 1000s have sort of got the ball rolling on flat Earth and all that, and incredible stuff with that. And so but I think the cool thing about drones, though, that's again, drones are just coming out more and more, and they're not going to get more and more expensive as time goes on. And so as they become more and more affordable, I feel like they're going to be the thing that's going to help us, sort of common man, come up with a rigorous test for evaluating the curvature or lack thereof. So I'm going to talk about what I proposed on my channel. This is a very simple thing. Again, if we had a military grade drone with the precision of military based GPS, this test would be very, very straightforward. But conceptually, it's just basically taking a drone with a camera on it pointing downwards, and then suspending a ball from it, and ideally not a chain, actually, like an actual rigid pole or something would be nice. And so essentially, from this starting point, if we can reliably move the drone in a straight path, or in a predetermined path is a better term, then it will interact differently if the Earth below it is flat and level, or if it's curve. So if it moves in a straight line, and it has to be reliable, and I understand there's error bars associated with that, and we can talk about that. But essentially, if this drone moves along a straight path, that ball will continue to remain, submerged in water. So on the flip case is that if you do have a curved surface, which Ball Earth claims, the ball would start underwater. However, if you go in a reliably straight flight path, at some point in the future, in the distance, that ball will have to come out of the water, because the drop distance is increasing. And the nice thing about the camera is that you could actually take a picture of the ball beginning submerged in water, and then eventually coming out of the water, and then take a picture of it. And then if you can use a ball that's like thermochromic, if its properties are different underwater as above water, it could actually change color and sort of highlight it even more. And so to me, this whole thing is not necessarily drone dependent. It's more just establishing a coordinate system that allows a device, doesn't necessarily even have to be a drone, to move in a predictable path. And again, I'm not saying that's easy, but the thing that I presented earlier could be sort of the foundation of developing, a flight path using GPS. So that's one way to do it, just strictly based on a pre-planning of GPS. But Another way to sort of add on to that, to sort of reduce the variability and the risk of this test not giving meaningful results, is if the drone can be equipped with a laser. And I understand that lasers have properties that are not ideal and not perfect in in the longer portion of it, but locally we can assume that the laser shoots in a straight line. And so if we can do multiple drones, and it doesn't necessarily even have to be two, but multiple drones with lasers to sort of guide the flight path on top of an already predefined path, could help us get even more comfort that the drone is flying in a predictable path. And so to me, this can be done in sort of a daisy chain where you just, you have drones that are paired and coupled together tightly, and then again, honor a predictable flight path. And so once you have an electronic device, whatever it is, flying in a predictable path over water for enough miles, that to me, theoretically, conceptually, will solve this debate, because the shape of the Earth beneath it is obviously different, two different scenarios. So whoever solves that, or if this is the avenue that people go, that's fundamentally what would need to happen. We can obviously debate the accuracy of it and all that, but the nice thing about, again, this is that it's very, very repeatable, and GPS in and of itself is a very, very repeatable system. We can debate its accuracy and its granularity, but it's very, very repeatable. So that's one test that I think that would be very, very cool, to get involved in. I'm not saying one person could do that, but if people get really, really serious about this, and then we crowdfund and that type of thing, we can get an engineering firm to design something like that within tolerances that they would communicate to us. And then again, if you can get a electronic device to go in a predictable path over water, to me, this thing will get solved fairly quickly. The next thing I want to talk about is wide angle lenses coupled with the drone, helicopter, and then using image processing. So we get a lot of stuff from ballers that like 0.5 degree, 1 degree is not noticeable in relative tilt between buildings. So I'm just going to kind of talk through that and then get George's feedback on it. So first thing I want to talk about, this is obviously like a cartoon, but this is the sort of setup. We have a drone equipped with a wide angle lens camera, or maybe just even a regular, just good camera. And then in the baller theory, two buildings that are sufficiently far apart would have a relative tilt. So I'm imagining, those buildings having a rooftop that's accessible, so we can shoot a laser up vertically to sort of highlight the orientation difference. But that may not actually even be necessary. As long as the two buildings are visible to the camera and all of that, I want to explore the option of being able to measure its relative tilt, or its alleged relative tilt. So this is sort of a picture of what it would look like. Like, I just got this from Google Images, but these two buildings in Manhattan are shooting up, some kind of light. And so essentially, if those two buildings were far enough apart, and we had image processing available to us, we should be able to measure and detect the relative tilt. So obviously, ball Earth theory, ball Earth defenders will have to say here, obviously, that those two buildings are very, very close together. And so, they are effectively parallel, even though on a ball Earth at a sort of microscopic level, they are diverging. But just to give you a visual, that this is sort of what I'm getting at. So the way I would sort of start this is that we would need a plot of a drone with a camera on it. And then we would need to understand that the farther it goes up, you would be able to observe more things just in general. And then you would definitely be able to then observe buildings. And then the way I see it is that the higher and higher up a drone could go, let's just say it could go up an infinite distance, you would get a point where you would see a lot of detail. And then at some point everything would collapse because you would not be able to see anything because you're so far away. So there's kind of like a diminishing return in terms of elevation. And so if a group could kind of survey this out and do a couple of tests and, elevate the drone and then do some sort of reconnaissance and see like which two buildings or structures can they see that are far apart, and then figure out what that maximum separation is, we would be able to get our what I call D max. So that is the maximum distance that a drone with a camera elevated at a certain distance called OH max could see. And then to me, this is a starting point. Then this is like, now we've kind of come up with what is the ability of a camera and a drone together, and their height allow us to see two items that are a certain distance apart. And then so once you have that observer height and then the distance of those two buildings away, you can then determine what that tilt should be of those two buildings, just using a very, very basic formula. Right now, I didn't include the arc distance, but just for now, let's just say that we can assess what those two buildings are, figure out how far apart they are in a fair way, and then we should be able to then compute their relative tilt, their angle relative to one another. And so understood that even a fairly vast distance apart doesn't produce much angular tilt, but I'm not just as an example, just to give you an example, at my golf course, I'm at 70 feet elevation, and I can see downtown Houston and West Chase, which is about 15 miles away, just with my own eyes. And so I can see a building in downtown and in the west side of Houston.
So sorry to interrupt. Just a little bit of a feedback. I've been reading the chat and following. Most of the people saying you're talking a lot and making a little sense. Some people is saying word salad. Some people is saying too complicated. Carry on. Just wanted to give you some feedback.
Okay. I think with the questions that maybe will come up after, I think that, and again, I can post the slides if people want to see it, but it's just kind of conceptual. Maybe people haven't thought of this yet, but to me, this is coming. It's inevitable if it doesn't get solved a different way. But so just all I'm saying is that there is the ability to see buildings far apart. That's not really that controversial. And so let's just say we are able to do this with a drone and a camera. Now the question is, how can we resolve the relative tilt? And so the argument of can you see 1 degree tilt, to me is very, very poor, because we can. I don't if people can see these two lines, even in PowerPoint can resolve two lines that are 1 degree tilted relative to one another. And so the idea is that, let's just say we were able to capture the tilt or two buildings that are sufficiently far apart using image processing. If you have these two sets of lines, the first two are perfectly parallel and the second two have a 1 degree tilt relative to one another, you can very easily use, image processing like MATLAB and, FFTs to distinguish between these two, because they're not the same. If you took an image of the first one and did an FFT on it and then did an FFT on the second one, you don't need to know what an FFT is, but you can do image processing on those two images, and they will give you different.
Is this how much difference of a degree are in this? Is in this one that
the first one they're parallel, Jose, and then the second one is 1 degree, and this is PowerPoint.
1 degree, okay.
Yeah.
So that's the equivalent of 69 miles of the difference, okay.
Yeah, if the Earth is curved, yeah. So you wouldn't even need 1 degree for MATLAB to give you different coefficients, but I'm just using this as an example. That whole 1 degree is barely noticeable, is not rigorous, because image processing could very, very easily do that. I think the issue is edge effects and all that. So the wide angle camera would have to image something further than just 69 or 70 miles. So that's a fair statement, because the edges might not be reliable, but being able to distinguish 1 degree tilt to me is actually not a very hard thing at all. So that's what I was thinking about relative tilt. So I just got two sort of quick points, and then I'll pass it on to George. So this one is a bit more qualitative, but what I was thinking, again, possibly leveraging that GPS idea that I mentioned earlier, sort of regularizing the grid, is coming up with an app or just some database or place where people, ball earthers and flat earthers alike, can put the time, the date, their GPS location, and any time that they see the sun and the moon in the sky together. And so they don't have to tell us obviously where it is or anything like that. Just that they've literally identified the sun and the moon in the sky together. And I see it, regularly, that occurrence. And so if we can create like sort of a database of those sightings and then filter them by time, date, remove any anomalies that don't make physical sense, and then plot them on two different surfaces. Again, I obviously don't know if this will work, but I just put that out there as an idea that something like this is more qualitative. But to me, again, over time, something like this would be interesting, at least to see the results plotted on two different surfaces. So the very last thing I wanted to talk about, which might be the thing George wants to sort of focus on, but is Sly Sparkane's water level test. And I call it the walk-on water test. And I'll explain what that means. And that just to give people a quick update on what Sly is planning to do, he's essentially creating a network of tubes that will be filled with water and be spread, a long enough distance where it'll effectively create like a water body, but sampled every certain number of meters or whatever. And so,
sorry to interrupt one more time.
Yeah.
You want to do your whole presentation first and then George, because you've been going for like 25 minutes, Yeah. I thought we were going to do maybe like 10 minutes or 5 minutes.
Yeah.
Jose, go ahead, carry on. It's the two of you only. I'm sorry to interrupt.
That's okay. I'm taking notes.
It's a good point. We just we just agree to go through the whole thing, and then we can kind of run past things, but run over things again. But
no, go ahead. I'm taking notes. I can follow.
Okay. So basically, Sly's test is if you just think of like a water body, and then he's sampling it for those engineering people out there inclined. He's sampling it every certain distance with tubes, and so it's a closed system in the sense that the water can only flow within that system. And so essentially what you can do with that is use the properties of water as a level, and then from that you should be able to observe a curve if it exists. And so the one thing I would like to add, and I'm curious to get George's feedback, is like, I don't really, not that I don't trust the test, but I would like those levels transferred to the ground. I want a sort of tattoo of those levels on the ground so anybody can come back and look at them. And so this may not be possible, but this is what I propose, is sort of a transform, almost like a coordinate transform. But I want that level on each of those tubes to be repositioned and transferred to the ground. And so I propose, having some fixed angle and then having a device with a laser at the end shooting from the level in the tube down to the ground. And so in a flat earth scenario, you would get the result that I show in the top view. You would get the blue water levels on the left and then the red laser mark on the right, and it would be on the ground. So everybody could come back and see, like, look, this is a straight line. This could only happen on a flat earth. And so in the curved earth scenario, you would get the red dots leaning, curving to the left. And so essentially what this is basically taking the tubes and then pushing them over to the ground. And so you could physically see those red dots on the ground, and then anybody can come back. Again, I'm not sure you can make a permanent mark, but I would just physically would like to see those on the ground. And then so people could come back and do their own sort of leveling. And then the nice thing about this is that you can use multiple techniques now to create the top and bottom lines to come up with that window that he's planning to make to determine whether there's curve or not. So that's just a one little piece. I'm not squabbling over the test. I think fundamentally or conceptually it's good. I mean, it would be observing a real phenomena, water bulging. But my only thing is that with this, or if there's some other way that George and I or others can come up with to transfer those heights of the water to the ground. So my very last point I want to make, and this is just what I see happening, is there's a lot of talk and stuff. I just want to now sort of go through what I feel like this will start happening, is that we're going to have people who have debates. But I think what's going to start happening, again, with technology available, is we can now come up with a mutually agreed upon test, even if it's not able to be done by us, but by engineering firms or others. And then we can crowdfund And then it's kind of fun when it's not just two people, doing it. I think this is kind of cool if everybody, has an interest in a particular test and then they think it's better for them. They can put money behind it. And then the nice thing about this too, you can outsource it and then go to engineering firms and many of them, different ones, and allow them to sort of give them the specifications and the tolerances, and then allow them to determine what the result is. And then there could be a sort of financial leveling up, pardon the pun, afterwards. So this is stuff that I sort of am more interested in. Again, if people want to engage with me in any way, or I have a feeling there's more people like me that want to move this past just concept and into engineering based tests. So sorry if that was long winded, but that's my slides. Those are my slides.
Thank you very much, man. I really appreciate it. People was yawning like, "Oh my God, when is this going to end?" Just keep it funny. All right, I'm gonna stop presenting you.
Yeah.
All right, go ahead. I'll mute myself. Silence.
No, I thought George was sorry. George, do you have any thoughts or anything? Apologize if I went quickly.
Yeah, actually, I do. Are you finished now?
Yeah.
Okay. What I'm going to work backwards, since the last of what you talked about is fresh in people's mind. In a little bit here, Jose, I'll want to start presenting. But one thing is I tend to be a little bit dismayed at flat earthers always want to seem to be using lasers. They regard lasers as kind of a silver bullet, and it really isn't. Lasers have a problem with the beam spreading out. It's called divergence, and the beam of a laser does not remain pencil thin indefinitely. A typical handheld laser has a divergence of 1 milliradian, which is 0.0537 degrees. And if you're going to try to, say, set up two lasers pointed vertically to try to detect a tilt, that's not really going to work, because with a 1 milliradian divergence on two laser beams, you're looking, this is equivalent to having the lasers separated by a minimum of 4 miles before the beams start diverging, where it'll swamp out any tilt that you're trying to detect. And your thought about detecting 1 degree of tilt, it really is impossible. I did a video last week. You and other people that are interested in detecting tilt might give that video a look at. It's called Detecting Tilt. And I showed how hard it is to detect anything less than about 10 degree tilt, which would on the Earth be equivalent to 2 posts being separated by 690 feet. You pick up 1 degree of tilt on the surface of the Earth using the spherical model for the Earth. You pick up 1 degree every 69 miles.
But George, do you agree? Do you agree at least what I told you about, or do you disagree with my statement that I was at 70 feet Wildcat and I can see downtown and West Chase, so I can visually just see that without even a camera or more elevation?
Well, yeah, I mean, you can see things, but that's not tilt. I mean, sure, you can see far away the more that you're elevated, but that's not detecting tilt. Tilt is quite another matter. the other issue that you're faced with is, suppose you have two long poles separated by 69 miles, and so you're picking up 1 degree of tilt.
Yeah.
Well, if you go with, in any of these tests or experiments, you have to take into consideration both a flat Earth and a spherical Earth. Your test has to encompass both models. Well, if your test is going to encompass also a flat or a spherical Earth model, you're talking about 1 degree every 69 miles. Well, what kind of a drop do you get in 69 miles? Well, a drop in 69 miles, that's 8 inches per mile squared, or 8 inches times 69 squared. So that works out to 3,174 feet. That's for a pole at 69 miles away just to be peaking up above the horizon. I mean, it's just totally impractical, even with a laser beam. Trying to shoot a laser and see a laser after it's gone up close to 3/4 of a mile, you're not going to see it 69 miles away.
Wait, George, you do agree from an electrical engineering perspective, if you have an image with two parallel lines and one with a 1 degree tilt, the FFT coefficients will be different in both, correct?
In terms of what?
If you
you mean you're going to be trying to do some signal processing, but the thing is, how are you going to take into consideration the divergence of the beam, that just beam divergence, and then you'll also have diffusion because of the atmosphere, water in the atmosphere. The divergence is just a small part of the problem. You're going to have particulate matter and moisture in the air, which is going to cause scattering of the beam as it goes skyward from the surface of the Earth. You might be all right for the, several hundred feet or 1,000 feet, but once you start getting beyond that, you're going to have so much scattering in the atmosphere in addition to the divergence that it's just not, I just don't see it working.
Yeah, you may not, actually, you bring up a good point. You may not even need the laser beam. You might just need two very, very high physical structures. And so again,
well, I just told you, if you're going to try to pick up 1 degree of tilt on the surface of the Earth, say situated coming vertically out of a body of water, so that you're guaranteed that you have a surface that's following a nice smooth contour, those poles have to be separated by 69 miles, which means at a bare minimum, one of the poles is going to have to be over 3,000 feet long just to peek over the horizon so you can see it, to even try to begin detecting tilt. And then in 69 miles, you're just not going to see anything, regardless of what kind of magnification you get. There's going to be so much image blur and distortion that you're never going to detect 1 degree of tilt. So I just don't see that being practical at all.
No, fair enough. I think it's something that it would need to engage multiple experts. First of all, drone people, wide angle camera, and then image processing people. I think the image processing thing is the most sort of easy to understand and grasp, because you can just literally take image and run them through MATLAB and see. But again, I'm not saying that it's—
But that's fine. But if your image is distorted, no amount of signal processing is going to bring it back through atmospheric distortion.
No, that's the beauty of signal processing, George. That's why people do signal processing, is to recover.
Yes, to an extent, but you cannot reconstruct a nice straight pencil thin laser beam if it isn't straight and pencil thin. I mean, with scattering in the atmosphere, I'll just say I'm skeptical. Okay?
No, that's fine.
Very skeptical that you can do. You really need to watch my video about tilt, because I use precision surveying equipment along with visual demonstrations in my video, both with short poles in my hand showing you, and then also out using 3 10-foot poles tilted at various angles. And I defy anybody to look at those images and tell me that they can detect the tilt that when these poles at 441 feet away are tilted less than 10 degrees with respect to vertical. At 441 feet, you just can't do it.
It has to be side to side. I sure, like front to back.
Well, side to side doesn't work either, because I mean, as if you look out, your horizon is always, if you're 6 feet up above the ground viewing out at the horizon, your horizon, no matter where you swing around in a 360-degree circle, is always 3 miles away. So it isn't like being on a flat plane where you can set these poles up and then move a long distance away and see them all broadside. That's not going to happen on a spherical Earth, because your horizon is in a circle about you. It's not a straight line away.
So, no, but that's actually that's a good point. We're trying to eliminate these notions of a horizon, these non-physical things anyway. Like that's, but anyway, that's fine. That's fair enough. I'm not presenting a solution, obviously.
Yeah. No, I'm just trying to put it out there so you understand that these things are kind of rather difficult. I mean, the thing that has most merit, of course, is you talking about these drones with the GPS, but the difficulty I see there is I believe most flat earthers will not agree to that because you're using the GPS system.
No, the nice thing, not to interrupt you, but the nice thing about this, again, probably there'll probably be issues on both sides, to be fair, because it is not a very, it's reliable. It's how do I say this? Like, it's available. It is not necessarily always predictable, because it does depend on certain calculations that could change depending on its line of sight and all that, what's going on. But the nice thing about that type of thing, and again, I'm not advertising that too much, but like, you can go and repeat these kind of things. Like, you could literally see a GPS coordinate physically there. You could touch it. You can take your phone there and hold it there.
Yeah.
You know what I mean?
Okay. So, but CP, here's the deal. All right, let's imagine you're going to be establishing coordinates along a straight tangent line out from your starting point with these GPSs. So you have to get these GPS or these drones positioned so that they're all in a straight line from your starting point. Okay. Mm-hmm. And then you drop your ball on a chain or rope or whatever, and go along this tangent to see if the surface of the Earth remains at the same height with respect to the ball, or if it starts falling away from the ball as you go along this straight line. Well, this has basically already been done by Jesse Kozlowski in many different venues. He's done this basically on Lake Pontchartrain with Soundly. He came up here last winter with Soundly, and we did it on the on Rainy Lake here. And most recently, I understand he went out to the Great Salt Lake with Tim Osman, and also did the thing there. So Jesse has extremely accurate GPS equipment. I mean, he can measure elevations and position to within centimeters, or I think even probably within a couple centimeters, probably even better if I remember right. But it's no worse than a couple centimeters. So he has this equipment to do it. So if you're going to go and rely on GPS, why not just rely on what Jesse has already essentially done with his? I mean, the only difference that you're looking at here is you have this more of a visual indicator that you seem to like. I can appreciate that. But on the other hand, you're relying on positioning these drones to an accuracy that cannot be attained to the degree that Jesse has with his equipment in establishing a tangent line and then drop. We did that out here. He confirmed all my measurements using he and I went out on the ice with his GPS.
Yeah.
And set his GPS receiver at the centers of my targets and got the 3D coordinates of the centers of my targets, so you could measure precisely as a confirmation to my own measurements, where I use the steel tape rule to measure from the centers of the targets down to the surface of the water. He also used his very precision GPS equipment for doing that. So essentially, he was establishing a tangent line with his GPS and measuring down from that tangent line, just like you would be with the drone, indicating with a weight attached to a rope or a chain or whatever. So it's been done in different ways using the GPS system. So nothing is really being gained with the drones and positioning them with GPS, other than it's giving you more maybe of a satisfying visual indication.
Can I get a warning? I got some feedback, maybe a concern. Hang with me. I'm going to try to phrase this the more logical way possible. I still can't pass my mind past the image you showed with the 2 poles with the 1 degree differential in the top and in the bottom. You show one set parallel and one set with a little deviation, right?
And you could see it, right? Could you see it,
yes.
Jose? Okay.
We can see it. All right. So I try to, because I got a very visual mind, illustrative, right? So I picture this in a scale, right? If 1 degree in the globe model is 69 miles, I'm going to round it up to 70 miles. If 1 degree of differential is 70 miles, if I'm standing in the beach, right, I have to look 35 miles to the west, 35 miles to the east, so I can see the 2 buildings. Even if I do a panorama and it's all perfect, the building, even if it's 1 mile high, 1 mile high, 35 miles to the left, another 35 miles to the right, it's going to be no way to perceive this half of an angle of a difference between one and another, 1 angle of difference. There's really no way. Even if you make the building 69 miles high, 1 in the left, 1 in the right, you're not going to be able to perceive this. It's just too minute. I mean, just perceivable. If that's the way I pictured it in my mind, scaling it up.
I appreciate that. I guess all I'm bracing both sides for is that more of these discussions are going to happen. And so I'm not trying to be a prick, but this is the way it's going. It's going technology. Obviously, the foundational underpinnings are there for both sides, but no one, and not even me, I don't recommend anyone, you just accept my proposed test because they're just words, but also don't accept what Jose just said, because he doesn't know that. He doesn't know the sophistication of image processing. He doesn't know wide angle lenses or drones. We're all learning about these things. So I'm not saying this to be rude to him, but what he just said is actually, he cannot back that up, at this point.
Well, the other thing that we haven't even discussed regarding this sort of thing, I mean, I talked about divergence, scattering in the atmosphere, absorption, this sort of thing. But we totally ignored, the effects of refraction over those sorts of distance. Refraction is just going to kill you. Even with standard refraction or minimum refraction day, you go over those sorts of distances, and refraction is just going to totally wipe out any 1 degree difference in tilt that you're going to be trying to perceive. Now, the thing on GPS is I'd like to make a comment about, especially with people using their GPSs in their cell phones and having handheld GPSs.
Yeah.
Unless you invest, tens of thousands of dollars in a GPS system.
Yeah.
These GPSs do not register elevation accurately at all. I have used several handheld GPSs, fairly expensive ones. I mean, for the layman.
I got a quick question. Question from the chat. What is the best precision a GPS can get?
Well, I'm just getting at that right now. That's what I'm gotta just briefly for the people out there.
Wait. Ask Rumpus, because he claimed that my test it doesn't have, and he's
No,
very
please. Hey, I didn't interrupt you during your
All right,
discussion.
fair enough.
Please, is handheld GPSs, whether in a cell phone or a standalone unit, do not register elevation very accurately. That is the worst measurement. You have longitude, latitudes, longitude, and elevation. Elevation is the worst of them all. My handheld GPS, which is a $300 unit, at best gives me about a 50-foot elevation accuracy. And I can register degrees and latitude and longitude to the 5th digit. For example, I'm at 48.61378 degrees north by 93.30622 degrees west.
Wow.
Now, I have found after testing my GPS for years, I have statistically determined what I call counts. That's the number of digits that you can vary in the last position. That's at the 5th decimal point. On latitude, I can vary as much as 12 digits on the last digit, on the 5th decimal place. So that would be like 48.61378 plus or minus 12 in the two positions. So it could be in the last position, it could be 78, or it could be 90, or it could be 66. And what that basically boils down to is that my latitude, see, on longitude, everybody has the same number of miles per degree on a longitude line going north-south. That's 69 degrees per mile. But latitude depends on your latitude, where you are. I'm at 48.6. So 1 degree at 48.6 translates to about 2.57 feet per last digit on my GPS. And at plus minus 12, I'm picking up basically around 30 feet of uncertainty, plus or minus 30 feet uncertainty on my GPS. Now, if you think your GPS is accurate, there's 2 tests you can do to see that what I'm saying is not BS. Is take your GPS, go to a spot, around your home, put a stake in the ground or a rock someplace, write down the coordinates, then turn your GPS off, and then turn it back on and let it reaccumulate the satellites and notice the position. You will see that you do not come back to the same position. You'll probably be as much as 10 to 20 feet off from what your position was when you
agreed.
Before you turned it off. And then the other way to do it is note your position, then walk north, south, east, west, walk away 500 feet and come back and see the position to the same position. So with those 2 tests, turn it on and off and walking and coming back, you'll see you do not come back to the same coordinates. And if you do that several times, you'll get an idea, if you mark down the variation, about, what the uncertainty is on your GPS. And I guarantee you're going to find you're going to be anywhere from 10 to 20 feet of uncertainty in your latitude and longitude. And with elevation, you're going to be as much as 50 feet of uncertainty using a handheld GPS.
Yeah, George, I appreciate that point, but at least conceptually, you agree with creating a grid. Let's say we have like 10 football fields all together. Again, I'm not giving you the work to do or me.
No, I'm saying
do it, right?
With the proper equipment, you can do it. Stuff like Jesse Kozlowski has. He can measure this stuff to within a couple centimeters. Yeah. I'm just saying you can't do it with a cell phone. You can't do it with a handheld.
Agreed. Yeah. I think that point, again, so just to give people context, our discussion was like, infinite money. Obviously, there isn't infinite money, but like infinite time and all that. So George makes a very, very valid point that for that, to be kind of useful, or to be able to draw conclusions from that in a fair way, you need like, more expensive equipment, which is fair. I think that's why I think engaging third party people, people who specialize in that is fair. But the thing I like about that is, again, GPS, using it doesn't have to necessarily be in the way I propose, but it's available everywhere, and like, that's the cool thing about it. And then it's very, very hard to refute a test like that if the grid is even possibly visual, and you could go and verify it, and then a path is used based on that as the platform, and it's localized. Like, it's not based on the sphere Earth or NASA or anything like that. It's purely just a local grid set up with an origin, and then a direction established in a fair way. And then if a drone flies honorably along a path, I think, I don't want to put words in George's mouth, but like, conceptually that could solve the problem. Again, I'm not saying it's easy even beyond that point, but once you have a grid that's accurate and you could check it, and it has certain error built in, and then a drone or a device can fly along a predictable path, to me, that will reveal the shape of the Earth.
Jose, I'd like to start presenting if we can. I've got it to share.
Yeah. Please don't present the Hangout link.
Pardon?
Don't present the Hangout link.
Oh,
present a window.
no, it's blocked out. It's blocked out.
When you're ready.
Yeah, I'm trying to share it here. It doesn't seem to be taken for some reason. Shoot. Are you getting it all?
Not yet. I'm not receiving any screen share yet.
I don't know what's going on here. I had the same problem the last time. Oh, here we go. There it goes.
Cool. You're presenting.
You got it yet?
Yeah. Just don't show the. Yeah. I got it. Perfect. Thank you. I got it.
Okay. All right. Tell me when we
have you've been presented to everybody. Yeah, go ahead.
Okay. I'm just going to go quickly through the spherical Earth model, and then I'm going to talk about Sly's experiment. In principle, I'm endorsing what Sly is doing with conditions, and I'll explain what those conditions are here shortly. Okay, here we have, say, the surface of a sphere. This is the mathematics for finding the relationship of, if we draw a tangent, the red line here, to the surface of the Earth, and measure the drop distance down to the surface as we go along the surface of the Earth, some distance s, the relationship is exactly, this drop distance is exactly the chord distance from the observation point to the target, going this chord, which is going through the Earth, c squared over twice the radius. That is an exact equation. Now, if we approximate the chord distance with the distance along the surface of the Earth, we can say that this drop distance is the distance along the surface squared divided by twice the radius. And if you put the numbers in, that the radius of the Earth is 3959 miles, you end up getting 8 inches per mile squared, where S is in miles. And this approximation of using the arc length distance rather than the chord distance gives you very little error for any practical measurements you're making. This is the equation for error. The percent error is the distance along the surface of the Earth, S in miles, divided by almost 2 million, 1,960,000. So for less than a tenth of a percent error in the actual drop distance, or that your distance has to be less than 443 miles. And if you're willing to pick up 1% error, this equation is 8 inches per mile squared along the surface of the Earth is good for up to 1,400 miles. So for all practical purposes, this equation is good for any practical measurements that you're going to make. Now, Sly's experiment is this. Suppose we have the surface of the Earth. That's this brown. The surface of the Earth is not smooth. We can have some dips, we can have some hills, and we're going to lay out some pipe along the surface of the Earth and then have some vertical risers at prescribed distances. Sly was saying about maybe every 1,000 feet or so. And you have these pipes connected, these vertical risers, by a long pipe that you pump water in, and you fill up these pipes. You let them fill up to a level and reach equilibrium. Well, what I'm showing here, the brown is the surface of the Earth. Here, I'll expand this out a little bit. You can see that you have a roughness to the surface of the Earth. And what this line is, this heavy line, is a average, a mean value for the surface of the Earth, and which is a gravitational equal potential. Think of it as a mean value for the surface of the Earth. And then I have two parallel equal potentials here that are parallel to this mean. Now, what we're going to do is we're going to start pumping water into the pipes. So what will eventually happen is water in each of these vertical risers is going to reach a level. Water seeks its own level. Now, if we have, say, a little bit of a hill here, and we pump water to bring it to this gravitational equal potential, then the water level is going to stop here. It has to go up the hill. It won't go past the hill at this height. If we wanted to pass this point, we'd have to pump more water in here. But let's, at this point, say we've pumped water, we've let it settled out, and now all these water levels are at an equal potential, gravitational equal potential. What we say, it has sought its own level. Now, on a flat Earth, what it will look like is this. If we take this uneven contour and have it on a flat Earth, then all the water levels, of course, will all be in line with one another on a flat Earth. That is the difference here. On the surface of a spherical Earth, these risers are going to be, dropping down from where the observer is as you go along the surface of the Earth. Now, on the flat Earth, if we set a tangent from the first riser water level to the last riser water level, all the other water levels will be lined up. Whereas on a spherical Earth, if we draw a tangent out from the observer, this where Mind of God would like to have his drones go, say at this position, this position, this position, drop a line down. If the drone was going along this line and dropping a line down, the distance between this weight that he has and the top of the water levels would never change as you went out on this tangent. Whereas on a spherical Earth, it will change. It goes as the square of the distance. This drop distance continues to get a larger and larger distance as the square of the distance out. Now, if we were to look at this, this is the sort of thing you have happening on the surface of the Earth. Now, I've just filled the tubes to the next level here. So we see that we've let it settled out. all the water in each of the risers is at the proper height for water level. So now what we do is what Sly is saying he'd like to do is sight up the first water level with the last water level. This is a visual indication that if you do that, and if you're on a spherical Earth, then the risers in between the first and the last will appear higher than the straight line distance between the first and the last. Whereas on a flat Earth, they'd all be lined up with one another. So this is a go, no go test. If you sight a tangent line or a straight line visual indication from the first to the last water level in the risers, then all the risers in between, if it's a spherical Earth, will appear higher than that straight line of sight distance between the first and the last. Now, I've done something similar to this, which I'll get to in a little bit, where if you set a tangent out, you can actually measure these drop distances and then compute these drop distances, do some curve fitting with each one of these drop distances with a given distance, knowing the distance out from the observer, you can see what kind of a curve it fits. Well, I have done this on a frozen lake and found that these drop distances indeed do fit the 8 inches per mile squared. Now, in the caveat that I have for Sly is he's proposing to do this over 1 mile, and I do not believe it's sufficient. And this is the reason. For a 1 mile test, if you're to lay this out and you sight between the first and last, the largest bulge that you're going to have in the middle for a 1 mile length between the first and the last is only going to be 2 inches. That's what you're going to be looking for. And that is going to be extremely hard to sight. And I'll show you some photographs that I have that can show, that will illustrate how difficult this is going to be to sight. My proposal would be go out to 3 miles. If you go out to 3 miles, then the bulge in the center, what you're going to be looking for is about 18 inches. That's going to be easy to spot. 2 inches is going to be really difficult given possible refraction effects. Even with precision surveying equipment, I found it difficult to measure few inches of curvature on the Earth within a distance of 1 mile. It's just very, very difficult.
George, can I make a comment really quick about that? No, the visuals help, man. This is great. Would you be against him doing the short range one and then using my idea of
no, he can do what he wants, but I think he's going to waste his time and his money setting it up for 1 mile. I'm highly skeptical that you can pull it off.
Okay, check this out. And I don't want to take away from the line of thinking, but if you could translate those levels to the ground and make it a permanent, and then you extend the test at a different time.
Yeah, I'm going to address that.
Okay,
I caught you on that. Now I'll talk about that in a minute. But anyway, now if we look, expanding this out, if this length here is 1 mile or 3 miles, this bulge that you're going to be looking for, if L is 1 mile between the first and the last, you're only going to be getting at most 2 inches of bulge between sighting a straight line between the first and the last riser. But if you go out 3 miles, you pick up 3 squared or 9 times more bulge. You get 18 inches of bulge. Now, okay, here we are. Okay, the pipes between the ends will appear above the chord that the observer establishes between the last pipe if there's convexity, a convex curve in the Earth. Okay, here we have our roughness of the Earth. Here's our average mean of the surface of the Earth, and you're going to sight from the first to the last pipe, the water levels. And then you have all these other pipes in between where the water, if you're on a spherical Earth, the water will appear above. The water levels will appear above, and all the water levels will be on this gravitational equal potential. So here's your bulge from the height of the water and the pipes to the chord that you're sighting between the observer and the last pipe. And of course, like I just said, this bulge is only going to be 2 inches if the distance between the first and last pipe is 1 mile, but you'll get 18 inches if you're 3 miles apart. Now, here's my proposal to fix this problem. As I say, here's how I would set it up. I say, go out to 3 miles, okay? And one of the problems you're going to have is purging the air out of this pipe. One of the problems that I foresee that Sly has is this pipe is too small of diameter. I'm proposing use 1.25 black poly pipe. This is an irrigation pipe. It's very popular for sprinkler systems, irrigation systems, and it's the sweet point for purchase price. We use it all out here. I used it a lot in Colorado. It's black poly comes in 3 grades. You've got blue, yellow, and red, and the grade just is a pressure rating. You don't need any pressure rating on this in this experiment, so you use the blue utility pipe, the black poly with the blue marks on it, which is the cheapest pipe. And then you're going to have a pump. Well, rather than pumping directly into the line, what I would do is I'd take a closed tank and I'd have the pump into the top of the closed tank, and then the feed out on the opposite end of the closed tank, feeding the pipe. The reason for this is it will help purge air going into the system. If you pump directly into the pipe, pumps have cavitation, they pick up a lot of air, and you're going to be pumping a lot of air along with your fluid, your water, into the pipe. But by doing this sort of a thing, what will happen is any air is going to, the water will come into the tank, and then the air will, rise up out. You have an air relief valve. So by the time the water gets to the other end of the tank, a good portion of the air would have already been purged all the water before it fills the pipe. Well, what you do is you fill the tank to all the way up, you close your air relief valve, and then you have a closed tank so that any water coming in will push the water out. Of course, that won't happen if you have air up here. But once the tank is filled, then the pressure of the pump against the tank will push the water down the pipe, and you will have a chance that the air will naturally purge itself out of the water. And you have a ball valve here, and you have a ball valve here. You close this ball valve until you close up the tank or fill up the tank, and then you open the ball valve and then let water flowing in. Now, a utility pump will generally run about, we pick them up for about $150 to $200. And if you're, well, let me get into that a sec. With an 1.25 black poly pipe, you're going to be filling 337 gallons per mile in the pipe, or 1,274 liters per mile. So you need a pretty good supply of water. And then I would say, I'll show you here. Let me just pop here. Here's the equipment. I've priced it out. You can buy 700 feet of black poly pipe for $240, $239.99. That works out to about 34 cents a foot. And then I would say you'd hook two of these together. What the way you do is you use these double male barbed insert couplings. You put one end in one section of pipe, then the other section in here, and then you use hose clamps. You tighten it down. This is how you do irrigation systems and sprinkler systems. So I'd say every 1,400 feet, then you could put one of these in. You could put 1.25 T and put your riser on here, and then you could put a clear pipe in here so you can watch the water level. This is a 1.25 to 1.25 T. This is 1.25 in line with a 1 inch. You can also get them to 3/4 inch. You can so you don't have to go with the 1.25 is for a riser. You could go say with 1/2 inch pipe or 3/4 inch pipe by using appropriate reducers. So what I would say is about every 1,400 feet, you put a riser. So going over 3 miles, you'd have 22 risers. Or no, you'd have 11 risers over 3 miles. Now, so every 1,400 feet, you put a vertical riser over the total length of 3 miles. And the weight of this is really quite formidable. You're going to have
Really
close
quick,
to
sorry to
1,300
interrupt.
kilograms per mile of water.
Sorry to interrupt. Really quick, feedback from the chat. They say the two of you are the most boring people on the community, and you're killing the viewership.
Well, that's fine. Go away then.
Go ahead.
You don't have to listen. Go do something else. Go play with yourself. Anyway, the base material cost of doing this sort of thing over 3 miles is $5,715. This is for all the pipe, the fittings, the hose clamps, and the pump, and the tank. And then I allow $1,600.85 for labor in helping to put all this together. So the estimated total cost on this would be $7,400. Now, one of the problems that you're going to have is I've had a lot of experience with irrigation pump, long lengths of irrigation pump. And what will happen is when you fill this thing up, it's going to take a long time to settle out because the water is going to oscillate back and forth. It's going to pump back and forth. If you have, say, 2 risers, the water is going to go up and down, up and down. And over this length, I figured it out, it's going to take probably close to 3 hours for the water to settle out and reach level and stop oscillating. Is the let's see here. So that's one of the problems. The other problem you're going to have, whether it be with this pipe or the pipe that Sly initially is proposing, is barometric pressure variations are going to kill you. Is any barometric pressure variations is going to cause the water to start pumping up and down. And that's another reason why you need to go a longer length, because if the barometric pressure starts varying, like if you start having a rising or falling barometer in 1 mile, this water is going to start oscillating and moving, and trying to detect a 2-inch bulge is going to be next to impossible. The other thing is you have to make sure is you're going to have to purge air out of this system. And so this is not an afternoon picnic. This is going to take several days, if not weeks, to do this test. You're never going to do it in an afternoon, even in 1 mile, because of this pumping, this oscillating that you get back and forth. The oscillation for this particular system on 3 miles, the period of oscillation is about 33 minutes. So if you had water on the far end on a riser and water here on the far end, if this goes down and this pumps up for come back to the same level here, it's going to be about 33 minutes for it to do that. In 1 mile, it'd probably be close, maybe around 10 minutes. It's pretty much a linear function of the length. So 2 things that you have to be aware of. You got to get the air purged out of the system, because if you don't get the air purged out, the air in there is going to act like a shock absorber and you're not going to get true readings. And then the other thing, like I said, with barometric pressure variations, this is going to likely pump up and down. So what we do is we put a ball valve here, and once the system is settled down, then you can cap. You have a ball valve here to let the water out or close it off on the end. So once you get all the air out of the system, you close the valve on both ends, and then you can cap the pipes, and then the barometric pressure won't bother you. And then once you have it, then you can drive stakes in the ground, and then have the top of the stakes drive them into the ground to the water level. So this addresses UCP as far as a visual indication. Once you get everything settled at each riser, you could drive stakes in the ground to the point where the top of the stake meets the water level on each of the risers, and then you'd have an indication without the pipes about where you're at. So this is the equipment here as far as the piping goes. Now, I did a similar thing out on the ice last winter where I set a tangent line and I put 2 sets of targets on poles, and the bottom set of targets were all at equidistance from the surface of the water, and then the upper targets were in line with a tangent line. So this way I could get analytical information rather than just a no-go, no-go visual observation like you have on Sly's test. Now, Sly could get analytical data if he establishes a straight line tangent from the observer on out and then measure these drop distances.
But wait, George, we got Rumpus in the chat just being Rumpus. Do you understand my transform from the level to the ground? Why don't we put them on the ground?
Put what on the ground?
Take the level and a fixed angle at each pipe, and then we can then take that level and put it on the ground. If the earth is flat and the level...
Wait, back up.
Yeah.
What level? What are you talking about, level?
Let's first imagine the case that the earth is indeed flat. I know that's hard for a lot of people to believe.
No, I can imagine that. Okay,
Yeah,
let me get back here.
Let's just say it's flat, and then the levels are all, forming the same height above some arbitrary point, right? Beneath them all. Let's say that's the case. And then you were then tilt this whole experiment forward and make, again, this is water, so I'm just like theoretical.
Well, we have 2 models here. I've got the flat earth model and the spherical earth model.
Let's start with the flat. So let's say that Sly's test is on a flat earth, and then it produces those levels, flat and straight. And so let's say now that you could push a button and then the water inside of them are all frozen, so it doesn't move around. Let's say you tip that thing forward, and then you drew a line on the ground. It would be a perfect straight line.
Well,
right?
Tilt what forward?
The whole experiment. Let's just say you could.
You mean these risers? You tilt them forward?
Yeah. Let's say in a magical experiment, you could tilt the whole thing forward and then rest them on the ground. You could draw a straight line across the levels, the top part, right? Do you agree with that?
No, I'm not getting what you're saying. You want to tilt this down so it's resting on the earth?
Yes, the whole experiment.
So each one of these you want to tilt down so it's resting on the earth.
Exactly. Let's just say you can really do that. I'm not saying it's easy, but first start with that. So,
well, no, it'd be easy to do. I mean, if you have a poly pipe, but I don't see what you're heading towards here.
All I'm saying is that
if we have all these resting on the ground, all these risers are resting on the ground. Now what?
And put a mark where the top of the water is at each point on the ground.
On the ground.
Yeah, on the ground. So you have a tattoo of where.
Like I put a mark here, I put a mark there. Okay, now what?
So you tilted the thing forward. There's the levels are fixed there. You put a little dot where each one of those tops are. So now you have a dot that represents the level on the ground. You see what I mean?
Okay, hang on a second here.
Yeah.
Just a minute. So I'll make sure we're going to do this right here. Just be patient here a sec.
Rumpus is about to have a heart attack.
Okay, here we're going. All right, so you're going to tilt this down. And we're going to put a mark here.
Will you guys want me to invite Rumpus for a few minutes before I shut it down for the question and answers?
If he calls me an idiot, I'm not. This hangout.
Just wait. Just be patient, Rumpus. I'm almost done here. Okay, so we've tilted these down, and I've got marks on the ground now. Okay, now what?
No, but George, right in line with where they are. Oh, you're doing it as if it's kind of in an angle, right?
Well, you're tilting it down. You said you want to tilt these down so the tops.
Yeah.
You mark where the water level.
Yeah. Yeah. I see. Yeah. So
now what?
So now the nice thing, again, it doesn't really change the experiment necessarily, but it's like you put the results on the ground and then anybody else can come by and then you can now use those if you were to increase the length of the test or sample more. You could like have those marks still there. You know what I mean? Like you can still reuse them.
What does that buy you? I mean, if the ground is rough and it has hills and valleys, and I mean, these marks are meaningless. They don't mean anything.
No, I just think, again, I'm not maybe for this test, but I think down the road, let's say, again, you have a drone or something that can go above this and have it. But
again, it doesn't mean anything. What I'm proposing, what I say is after you have the water level, you just drive a stake in the ground. So the stakes are at the height of the water. And you can do that here on the Earth. You just drive stakes in the ground so that the tops of the stakes.
Okay, fair enough. Sorry, that's fine too. Yeah, that's okay. As long as it's physical and it's there permanently, that's fine. Yeah.
Tilting these down doesn't buy you anything. I mean, what you want to do is drive some steel rods into the ground with a sledgehammer until the height of those rods match up with the height of the water in the riser.
Okay. So I like that. That's good. That's good enough. Yeah, fair enough.
All right.
Yeah.
All right.
Thank you. I just worried though, George, that he was doing everything with the thing set up. And again, water, it's variable, right? Like it's just changing. And it's like, once you have those things in the ground, other people can now come and, look at it visually. So, okay.
Well, anyway, so if you're on a body of water, like a large lake, like I'm on, and you have these sets of targets, you have upper targets that go along a tangent and then targets that are equidistant above the surface of the water. We have two types of tests going on here. We have a Bedford level style test with the lower targets, and then we have a set of targets that are going along a tangent. The ones that go along a tangent, we can get analytical information as to the shape of the contour of the Earth's surface. If all these distances are equal, are the same, regardless of how far out we go along the surface of the Earth. Here we go a distance S1 to the first rise target, S2 to the second set of targets, S3 to the second. If these distances are all the same, then you're on a flat Earth. If they're not all the same, you've got analytical data that you can crunch to determine the nature of the surface of the Earth. And this is what I did last winter. Now, I'm going to show you here why I think 1 mile is overly optimistic. Here are sets of targets that I had set out on the ice. This first target is 0.694 miles away. So this is 3,644 feet. This target, the dimensions from bottom across this dimension, the vertical dimension, is a little over 8 inches, and it's about 24 inches in length. This white distance represents 2 inches. I'm at 60x zoom magnification. This black is 1 7/8 inches, and this is at 0.694 miles. Now, the second set of targets is at 1.365 miles. We're out at 7,207 feet. That distance from here to here is 7 5/8 inches. So you can imagine 1/4 of that is 2 inches. So going out 1 mile is going to be in between these two targets. And if you're going to have a set of vertical risers, it's going to be very hard to convince anyone that there's a bulge there. Here's the same photograph.
But wait, George, what's the trade-off for the people listening? Like, if you make the test longer, what are the risks associated with that? Let's say there's infinite money. Why would someone
it's just
not?
cost. I mean, like I told you, you could. I padded it. The material cost was about $5,500. I added, another $1,400 for labor and setting the thing up.
But you think the water could flow through that pretty long network? Like, in a way, there's a way to do it if it gets longer and longer?
Sure.
Okay. No,
sure.
I'm just asking. Okay.
Yeah. I mean, you could do it longer. I mean, with 1.25-inch pipe, I would think that my gut feel would tell me you're probably good to 4, maybe 5 miles. If you're trying to go beyond that, you're probably going to have to go up to 2-inch pipe. And 2-inch pipe is really expensive. The 1.25-inch pipe, black poly, it's polyethylene.
Mm-hmm.
And that's the sweet spot, because 1.25-inch is commonly used in sprinkler systems and home irrigation. Like I said, it's about 34 cents a foot, and that's buying 700-foot rolls. If I were to buy from Menards, like I did, where I'm buying 22 rolls to go 3 miles, I'm sure I could probably. I haven't talked to Menards about it, but I'm sure Sly probably has supply houses in Germany. I think we could probably get that price, down maybe a nickel a foot, maybe even more, buying in volume, buying 22 rolls at 700-foot rolls. You could get a discount. Usually price breaks occur at 10 units and above,
Yeah.
So the next price point, I think you could probably maybe get a 30%, 20% saving buying, 22 rolls. I don't know. I haven't checked into it, but I just went with the price per roll, which is $240 for a 700-foot roll.
George, my point, just to go back quickly to mine, just again, I don't want to keep harping on this, but let's say those sticks were fixed, there, and anybody could come buy a ball earther or a flat earther. I would, and maybe not cheap, but the whole idea of me putting it on the ground is if you could have something fly above it and then literally see it, you don't even need to calculate it. You could actually, there should be a way we could actually see the curve without even needing the.
Well, you can. I mean, if you do this sort of thing, if you go out 3 miles, the amount of bulge that you're going to be picking up in the center is about 18 inches. You're going to see that through a spotting scope easily.
No, I don't want a scope. I mean, visually, you could just literally see it, like if you were flying over it.
No, if you're flying over it, you're not going to see it, because you're going to be looking straight down. They're all going to look the same. This is going to be the same thing as trying to spot tilt.
And we have been joined by the Rumpus. Hold on. We have been joined by the Rumpus for a question and answer section before I close the hangout. It has been good. Let's keep it simple, guys. Go ahead.
Sure. Let people in.
Yeah, I'm just gonna keep this close. We're gonna get the Rumpus. If you got questions, answers, concerns, please let them out. I'll mute myself.
Oh, I'll let George finish. Has George finished yet?
Yeah, go ahead.
All right. Okay. Well, I just thought a couple of points about some of the. Can you see my screen?
Yes, sir.
Just a minute. I got it.
Please don't share the hangout link, Rumpus.
Oh, yeah, I'm not. No, I'm only sharing the application window. I'm not sharing the screen. I'm only showing the illustration program.
Cool. You're presenting.
Right. So this is the situation with Sly's experiment. So what he's going. So here we have he's going to try and generate a series. He's going to try and put up these poles So this is on the curved Earth scenario. And he's going to try and draw a straight line between the, if you can see my pointer here, between this point here and here. And then he's going to draw, then using the camera, he's then going to position his other markers on the poles between them. So then, having done that, he then, in his, although this is flawed because it won't be straight due to refraction, but if we just eliminate that, don't worry about that for just a moment. Let's assume that by aligning a particular position. So, well, the way he's done that, of course, perhaps I should mention, he first of all gets the water level at each end, adds on 5 centimeters, and then he takes that marker as 1 point, and then he does the same thing at this end. And then having got these 2 end points, the end markers, by adding on 5 centimeters to the water level, he can then draw his straight line along here. Right, so then the only thing he has to do as an exercise in taking data is measuring these Y5, Y4, Y3. In other words, the difference between the water level and the line that he's created. So why on earth, mind of God, I mean, is going on and on and on and on about putting something on the ground is beyond stupidity. This data here is the data. And the fact if you put that data on the ground is using, and he was talking about using some sort of projection, which didn't account for the topology of the land underneath. A completely stupid thing
I
to
think
do.
we've killed that by driving stakes.
Okay,
I still
just
want,
unbelievable, just unbelievable stupidity in
I want to
action here.
explain it. So let's just again, just at least.
Well, let me just finish my point. I haven't quite finished my point yet. And so this data, this Y5, Y4, Y3, Y2 is the data. And he could, if you want to, he could write it down on the ground if you like, and say, for here, I'm going to put this down here for mind of God on the ground. But that's the data. Now, if you're worried about the veracity, whether or not the fact that there's a permanent thing on the ground, well, he could fake the thing on the ground. If you're worried that he's going to tell you fibs and he's not going to give you the real data that he's generated, well, he's going to make a video of this, of all the him collecting on each one of the data on each pole.
You're not understanding my point, man. I
am understanding your point perfectly.
You're talking with all your emotions and a bunch of
no, you're just
gibberish.
It's the only thing you talk about is emotions. You don't seem to have any idea of the practicalities of what.
Well, why don't you wait and let me go through step by step, and I'll explain what I mean.
Oh,
hold on. Your screen hasn't been presenting on YouTube. I don't know why. And I'm presenting to everybody, but your screen is not going through.
He didn't share anything new. Everybody knows the way the test is. He's rehabbing.
Oh, brilliant.
You want to represent? I'm going to stop presenting.
Yeah. Okay, hold on.
We know that. The hard part is.
No, you don't. No, we don't. Hold on. Let me. Right. So brilliant. That does that for some reason. The first time it does it, and then not. Right. Let's just try this again. Sorry about that, people. Right. It's very quickly. Let's just. Is it coming through now?
Let's see. Let's give it a few seconds. You see, I'm sharing your screen, and nothing is coming through.
Yes,
it worked for George, not you.
No, it seems to have to. I find that I always seem to have to do it twice for some reason. I don't quite understand why that is.
It's not coming through. That's weird.
It's just right. Is it? No, it's not. Still not coming through yet. Is it? Am I still not presenting? Come on, ref. That's got to be working. Just try that again. Whoops. So I muted that. No, I'm muting the wrong. Oh,
there you go. You got
brilliant.
It. Yep.
Brilliant.
Sorry about that.
No, my fault. It's probably my fault not sharing. Right, quickly, let's just go through that again. Right, so here we have Sly's experiment, which is with the random topology. This is the curved Earth case. So what he's trying to do, the key thing he's trying to do is to generate this dotted line at the top. And he does that by taking the pole at the start, adding on 5 centimeters, or the end pole, adding on 5 centimeters and putting a marker there. He then goes to the front pole, add on 5 centimeters, put a marker there. So he then has the 2 markers 5 centimeters above the water level at the far end and the close end. He then adds extra markers in between by using the camera to, in theory, generate this straight line, which of course won't be straight due to refraction. But we won't worry about that now. Then he measures these Y5, Y4, Y3, Y2, 1. He's going to make a video of it, so he's going to be measuring this so you can all see it. So why Mind of God thinks it's of any value to have this on the ground, as well as the fact that his idea of putting it on the ground was completely flawed because the topology on the ground will mean you won't have any sort of regular way of doing it. His idea of a transformer, drawing a line or a pole or whatever, geometric transformation, utter idiocy. So all you need is the data collected of these the slime would. And if you want a physical representation because you're worried about the veracity of what slime might do, well, he could go and fiddle with after he's done the experiment, he could change the thing on the ground. So it doesn't add to any credibility of it. So it's a completely stupid point made by someone who doesn't seem to understand basic logic. There you go. Right now, what's wrong with what I'm saying there?
You agree that this method is not perfect. Obviously, what George was getting at, doing something like this has issues with like not being long enough, the error being,
correct. Yes, I don't think it's got long enough. I agree.
I worry what you're going to concede with the way you respond. So we understand that. My thing is from again, I'm not even claiming to know what equipment could do this, but this is what I'm thinking is that you agree that, let's say your visual that you have right there, if you tip that forward, you would see that arc on the ground, correct?
Tip what forward? See, you're very poor at describing things. Tip what forward?
Yeah, that's fine. Let's say that the point where those tubes hit the ground and
hit down here, so below Y3. So this point here, can you see my pointer?
No, see where the blue pipes meet the network that feeds it.
Right down where the brown bit, where it meets the ground. Yeah,
exactly.
Where my pointer is. Why can't you see my pointer?
No, I can now. Sorry, now I see it. It's just small.
Oh, great. Okay, so I've got below the Y3 mark. So below the Y3 mark, where it meets the ground, I've put my pointer. I'll draw something there in case there's some doubt about it.
Do you mind putting
there
it
we go.
Those places?
Right, so there we go. I've drawn a big yellow circle here. Right, you're talking about something to do with this point here. Yes, right, what?
Yeah, all of them. You know where they meet? Could you put it on?
Okay, yeah, all right, all these points here. Right, okay.
Okay. Let's say that they had a degree of freedom where they could be folded down. Again, I'm not saying I know how to design that.
Why? The data is the Y5, Y4.
Just listen to my point. Fine. Okay, those points, right? Let's say you could tip those forward. You agree if you're looking
when you say tip them forward, when you say tip them forward, you put them on the ground.
Yeah, lean them like tip them forward. Like
why not tip them backwards? What's
either way,
I'm not getting what you're talking about, CP.
Yeah, you're not making any sense. Why would you want to lay them on the ground? Which I think what you're suggesting.
I haven't even got to why. You're still arguing about just being able to do that. How am I supposed to answer your question?
Well, it's a stupid thing to do because you can't lay it down on non-flat ground.
Let him explain. Hey, Rumpus, let him explain because I'm still not getting this.
I know it's stupid. It's amazing. Carry on.
Nah, it's fine. It's good.
Look, do you not understand that laying on the ground is all you're trying to do is to reproduce the Y1, Y2, Y3 values? That seems to be, but why can't you write them down on a piece of paper? Because that's the thing that matters. You've got the number. That's all you need to know. And can you not understand that lying something down on irregular ground makes no sense? For a start, you do understand that these water level is going to be a different. Let me just one more point, George. I want one more point. That you do understand that. One more point. You do understand because of the varying topology here that the water levels can be at different heights in the tube. Just because the base is somewhere is irrelevant because the topology is going to be varied. So the idea that the something measurement to the base is relevant is irrelevant, as well as the fact you're lying on some curvy ground. I mean, you don't seem to have the most basic idea of what's practical or how you measure things. It's amazing.
Rumpus. Again, the simplest thing to do is you go along these risers, you find you can drive a stake in the ground and bring it up to the water level or bring it up part way. You go along to make sure that you have enough clearance, say at the
but George, the height of the stake doesn't make any difference. It's relative to the ground you're talking about. That is not a measurement.
No, Rumpus, you're not listening to what I'm saying. All I'm saying is take your dotted line and say move it down so that it clears all the ground, and then you just drive a stake in to match up the dotted line. You can bring it down rather than having long.
Hold on, you're suggesting I do this. It says I move this one dotted line down to here.
No, the curved line. The curved
line. Okay.
Yeah, that curve that you claim to live on, Rumpus. We want to see that, dude.
Well, that's what the water levels are indicating.
No, what I'm saying is draw a parallel. Please, guys, let me explain this. Draw a parallel dotted line to the arc and bring it down so that it clears all the
So
rough topography.
when you say parallel line, right? So you want it to be a copy of that line?
Yeah, there
right?
you go. You could bring it, say, there, and then just drive a stake in the ground, so it's clearing all the high spots.
So
And
you
then
want to generate.
no, shut up, Rumpus. Jesus Christ. Let
This
me
is idiocy.
finish.
Dude, you're
All
lost,
I'm
man.
saying
Robert,
is if
there's
you don't
something.
want-
You're lost.
Hey, guys. Hey, come on, guys. Jesus.
George, you're basically talking about manufacturing a smooth surface that represents the equipotential surface of the Earth, building one up.
God, Rumpus.
How are you going to do that, George? How are you going to do that?
Yeah, I don't think you understand, dude.
Listen. God damn it, Rumpus. Just listen a second, will you?
You
Don't
can't do it,
interrupt.
George.
I'm saying if you don't want to have the risers with the water in, if you want indicators, all you have to do is take some steel stakes, pound them in the ground next to these risers. So either the top is at the top of the water level, or you could displace them all the same wide distance and say, drive them closer to the ground so that they are the, say, 1 foot below the top dotted line so that they all just match up with.
So you want me to draw a stake in here?
Parallel.
So you want me to put a stake? You want me to put a stake here?
Yeah.
Right. Let me just get.
Now, one way you can do it is bring the top of the stake up to the top of the water level.
Let me just get rid of these dashes. I've got it's in dash mode. Sorry about this. Let me just remove the dash part of this.
That's you and your goddamn computer.
Right. There we go. So. Right, you're suggesting we stick a foot. And what purpose does this?
I illustrated that. I showed you that.
What does it achieve? Are you just trying to record in some physical form this value here?
It's a physical recording of the water levels. That's all. Every riser has a stake like that, and then you can get rid of the risers in the water. I'm just saying, you don't have to do it. It's just a physical indicator of where you're.
But you're not
levels at each riser.
Right, but you're not saying this distance is any meaning of whatsoever. That distance there.
Huh?
You're not claiming that this distance
that?
has any meaning. That from the top of the stake to the bottom. I've got rather large.
Rumpus, get rid of those big arrows. Do another one at the Y2 position.
Right, but with that distance, which is the height of your stake, you're not saying it has any meaning to anything except as a record for someone who's coming along later. Has no meaning.
No, I don't care about that distance. All I'm trying to do is record the tops of the stakes.
Yeah.
The tops of the stakes are going to follow the top of the water levels, which will indicate the gravitational equal potential.
Well, you might as well just mark the pipes here and then just cut them off.
But I'm saying if you want to remove the pipes and remove the water, you have a physical indication.
Right, but okay, but we
you
do accept
have to do the stakes. I'm just saying so you can get rid of the pipes and the water.
So you're just basically copying what the pipe's doing, but this has no value it has no meaning except for so that someone can come along later and say
it does have meaning.
Well, it doesn't, because the thing you have to measure is the distance. George, the thing that makes a difference is between the dotted line and the top. So you'd have to work out where the dotted line was. You'd have to record that as well.
Rumpus, I'm not talking about making an analytical. It's a qualitative, not a quantitative measurement here. So then once you have all these stakes, you can go back if you want to sight between the first and the last, and you can see all the other stakes are rising above that straight line. We're not making any Y measurements.
But
you can do that later. You can do that with the stakes if you want. It's entirely equivalent to the risers with the water in it.
Okay, but I mean, it adds nothing. It's just
no, you don't get it. I'm saying, you don't have to do the stakes. All I'm saying is you want to record the water levels. This is one way to do it so that you can decommission the water pipes in the water, have the stakes in the ground to record where the water levels were.
Yeah, you could shift the next test in the middle parts and interpolate. So they serve a lot of value. Rumpus is just very emotional and it really knows nothing about anything. So it's not really useful to talk to him, actually.
No, well, Harmonica, you're not making anything useful suggestions. The recording of this physical thing does absolutely nothing for Sly's experiment. And the fact that you thought it did makes you an idiot, I'm afraid. The thing that makes a difference is the
Rumpus, no, you're really dense here.
No, I'm not. The thing that makes the only thing that needs recording.
Rumpus.
I appreciate what you're trying to do, George, is to put a stakes here that match the water level. We know that. We got that. I got that, George. I fully understood the point you're making.
Why did we bring you into the hangout if you're going to disrupt
because the only thing that needs measuring are these values. That's the only thing that needs measuring.
We have to close the stream with a boom. That how we invited Rumpus for a little bit of excitement. Thank you.
What's going on here, Rumpus? There's a qualitative and there's a quantitative. The Y's are quantitative. Shooting a straight line between the first and the last gives you a qualitative indication of the curve of the Earth.
Yeah, it's nice to have those there because we're gonna put those on the ground and trying to see it from a top view. We're gonna try and see it visually. With lights or lasers or something.
Oh my God.
We want to see the curve.
From the top view. In other words, if you had a plan view, you wouldn't see any difference.
Well, that's what I'm asking. Would you not see an arc and a plan view?
Not from a plan view, no. They'd be in a line. You wouldn't. Oh, Jesus.
No, that dotted line, that dashed line, if you project that on paper, it would be there.
Please, you guys, let me just say one other thing and I'll shut up. Because I don't want to fight you guys. Is I would recommend to Sly, rather than trying to line up a 5 centimeter line between the first and the last pole, is to get a accurate theodolite. The camera isn't going to have a set of crosshairs. With a theodolite, you could very accurately put a 5 centimeter mark on the first pole and on the second pole and line them up with the theodolite, and then have two people, one looking through the theodolite and another person going along to each of the risers with a target. And
that's what he's going to do. That's what he's going to do.
Your cell phone. Don't talk over me, Rumpus.
That's what he's going to do, though, George. You're just repeating what he's going to do.
But with a camera, I'm saying.
Yeah. So the only difference is you're saying a theodolite instead of a camera. Right. So the only thing you'll suggest. Right. So the only thing you're saying different to what he's going to do is with a theodolite instead of a camera. I completely agree with you. I completely agree with you.
Okay.
I completely 100% agree. He doesn't realize it yet.
Interrupting. Wait, come on, Rumpus. Don't.
Well, I'm just frustrated.
I'm just saying, no, you're interrupting. I'm just saying, rather than use a camera, you can get the positions, the Y positions, a lot more accurately if you're using a theodolite and put marks at 5 centimeters at the first and the last, line them up with a 30x theodolite, power theodolite, and then you have a crosshairs in there.
But George, he's not trying to
tell someone where to put the marks on the other remaining risers.
Right, but you do realize you don't need to use the theodolite to make this measurement, because all he's trying to do is to get the theodolite, or his camera in his case, is to position the marker.
Set up an accurate tangent line or an accurate straight line.
Yeah, that's the key thing. You kept on talking in your thing about using the theodolite or whatever or a camera. You would use a theodolite to make this measurement. You don't need to do that.
No, I did not say that. I said
okay. All right. Then perhaps I'm misunderstood.
I said to line up a straight line between the first and the last. You have a mark at 5 centimeters on the first and the last riser pole, okay, above the water line.
That's what I said at the very start of this presentation.
No, shut up. And
George, you're repeating what I said at the very start of this.
God.
You're just repeating exactly what I said.
Forget it. I'm done.
Right, okay. I said exactly the very first thing I said in this presentation was that you put markers at the start and end 5 centimeters above the waterline, and then you use the camera in Sly's case to position markers along the line. So you're just repeating exactly what I said, 100%. Now, I agree with you that the camera's not good enough.
Yes, but I'm saying instead of the fucking camera, you use a theodolite.
And I agree with you, George.
Through your head?
I agree with you 100%.
We're trying to measure this qualitatively and quantitatively, both. We're not just, you're just hung up on one thing. We're trying to do with different angles, views, different, we're brainstorming, dude. You don't have all the answers, dude. I guarantee you're not the smartest person in the world.
Well, I seem to be a lot smarter than you are, because the points you're making are absolutely ridiculous. And the idea you've said,
if you're so sure it's a ball, just go enjoy the ball, man. Like we're trying to come up with stuff we're
no, you're not. Well, you're trying to. All
you
the three
enjoy your ball.
All the three things you suggested were idiotic, I'm afraid. You had three ideas.
The thought of projecting it to the ground so we can actually see it visually from a top view is what to you? You think that's what?
Right. So you want to take a picture from. So your whole objective here is you want to see the curve as though
visually, yes.
But you could do admittedly, you could do it here from the side view if you really wanted that shot. You wouldn't need to lay it down on the ground. I mean, admittedly, I think in the situation that
we're trying to do both, man. Like,
what is the point of moving it laying on the ground? If you want this view, if what you're trying to achieve is this view here, but you're not though. All you're doing is you're duplicating and introducing errors. If you want the view we've got here on this screen,
we're introducing
really quick. Really quick. Let me jump in. When you guys are talking over each other and interrupting, nothing is being heard on YouTube. Wow. It cuts up big time, you know. So it's being a mess since one is talking over another.
Right. Mind of God seems to have huge problems in understanding simple geometry and simple logic. If you want, just by laying this down on the ground on its side, which is what you seem to be doing, then you want to take a picture from a drone. Well, if admittedly, you could have the same effect by just taking this picture, this image I've got here, which represents the side. Hold on. The side elevation I've got here. Hold on. The side elevation I've got here is all you're trying to reproduce by laying it on the ground. But you can do it from the side elevation. Admittedly, there are trees and things in the way because you need to get back. I think to get this view, which is 1.6 kilometers, to get this view with a normal angle camera, you'd probably have to get back about 800 meters.
You're a flat earther just bringing in confusion now. You're lost, dude. If you just figured out what I said now, well, obviously we know that this side view can be observed and understood.
But it's a pointless. But you keep on introducing these pointless exercises.
We're adding on top of the camera and those Y1s. We're trying to look at it from different perspectives.
Why? That doesn't change these values, does it?
Of course it doesn't.
Right. Well, then there's no point in it, is it?
We're adding a different view, different representation, some quantitative, some qualitative.
You've just agreed these numbers don't change. In which case, what is the point of messing with the poles, laying them on the ground, on a non-flat ground, by the way, which will not work?
Those Ys are unknown. That's the whole point.
They're going to be measured. Sly's going to go up to them with a ruler and measure them.
But
don't you understand that?
The whole point of this discussion was that there's errors in that. That's what we're trying to move on.
But you're going to add to those errors if you mess around with these tubes laid on the ground. My God!
We're talking about doing what you're saying. I'm not saying don't do it this way. I'm saying do yours. Put the stakes in the ground and put it. We're doing all of them, not just one. All of them.
So you think when Sly comes along with a ruler and he measures this value of Y3, you somehow think you're adding extra information if you lay this pipe on the ground. In which case the
Ys are only dependent on that top line being perfectly straight. There's error in that, man. Like that's
obvious. But if you lay them on the ground, how do you think you're going to improve that?
I'm just saying it's another view that people can now, if they have the ability to see it from the top view, there could be a way you could literally light up the curve and see it
on a curvy, topologically varied.
It doesn't have to touch the ground. It's just that curve needs to be like on the ground. Like it doesn't have to actually touch the ground. It just needs to rotate 90 degrees down.
Right. So
it's not dependent. If it can be moved and has a degree of freedom perfectly down, then that's all we need. That curve, we want that on the ground. That's my point.
So are you suggesting then they put a little marker where the top of this water thing is, and then lay it down horizontally?
Exactly. Yeah.
So right, but you're introducing extra errors.
I know. I'm saying do your point. I'm not against the first thing. Like the way he's doing it is great. I'm just saying as another thing, and then it's the nice thing about it being on the ground is if you run the test again in a longer experiment, you can still reuse those results. You don't have to
you can reuse the results anyway.
No, but I'm just saying it's nice because you're projecting everything physically onto the ground. It's going to add more and more comfort.
The ground is not flat. You cannot do. You don't even have any practical. If you claim to be an engineer, you don't seem to have any feeling for practicalities.
These tubes are not that big. We're not laying it over Earth curve, man. Locally, it's flat.
You think the ground, which is just a random piece of grass bank, is going to be flat? Do you?
No, I'm saying that's why I would use my angle transform with the laser on it. You could do that.
But you do realize that the distance between the so you think oh God. I just can't.
Just absorb the flat Earth
stupidity is just
for a
incredible.
minute. Just let it sink in, man.
No, you're just stupid. I mean, you're just. I'm sorry, but you're just proposing stupid things, George.
I think George has got. He has a headache. I think he's probably.
God, you don't need to do that because the measurement that counts is this measurement here. That's the only thing.
No, we appreciate that. We're
trying to generate images on the ground of a slopey thing is just introducing it's unnecessary for a start, and also it introduces extra errors. It's just completely pointless.
No. If you the whole thing is we're averaging out the error by looking at it with a diverse set.
Averaging out the error. You're just introducing additional errors. You're adding additional error. That doesn't average it out.
What I'm saying is,
you guys really don't need to argue this. If you put stakes in the ground, drive them into the ground at each riser equal to the water level, then you can do what you want after that. Who cares?
Let me jump in for 1 minute. Let me jump in for 1 minute. Sorry, hold on. Let me jump in 1 minute. I'm 2 hours near I'm 2 minutes near the hour time. I got visit in my house and I got a lot of mess going on. I'm gonna have to shut it down for today. I'm gonna share the Hangout link on the YouTube chat. Once I gotta close, I'm gonna give you guys a chance to say your final thoughts on how this went down. I'm gonna start with the Rumpus. He came in last. Rumpus, please don't go 5 minutes all in.
Okay, I'll be
get a little bit of a feedback and then mute yourself for the others to speak. Go ahead.
Right, all the points in Mind of God's presentation were idiotic, all of them. And he doesn't seem to appreciate that the thing that matters in this experiment is this value y3, y4, y5, etc. All the other thing is bonus. And doing things like messing around with the pipes and then making subsequent measures introduces an error. It's like making a multiple recording of something and then saying, oh, well, I'll then average out the results of my analog recording. You're just introducing extra errors. You want keep the errors to a minimum, and you make that initial measurement. Yes, there can be errors there, but any error measurement you make subsequently will have additional errors. The whole point about engineering is you try and minimize the things you do to something and get the purest measurements you can. And everything he said in his presentation was utter bollocks. Bye.
Thank you very much, Rumpus. Which one of you want to go first for the last thought? Yours or mine? Of God.
George, are you still here?
Yeah, I'm here.
Okay, great. Yeah, I mean, I guess Rumpus missed the beginning where I talked about diversity and doing things from different angles, different perspectives to try and, average out the noise. But so I encourage, obviously, the test. I think it's great. I think the camera and doing the leveling and all that is fantastic. I was trying to add another view potentially to this test and allow it to sort of be fixated on Earth, and then somebody else can come by and repeat it and compare and all that type of stuff. And this kind of feedback from the ballers to me is further confirmation that the Earth is indeed flat. Hope everyone's doing well.
Thank you very much, God. I really appreciate it. Go ahead, George. Final statement.
Yeah. Yeah. I lost my. Yeah. Is my audio on? Hello.
Yes.
Oh, okay.
Yeah, we can hear you.
Thank you, CP, for us having a discussion. And all I was trying to say is that if you wanted to have a record, a physical record that people can go back and play with if you want, is all you have to do is drive stakes in the ground such that the top of the stake matches the top of the water on each of the risers. And then you can decommission your pipes and the water and get rid of resell the pipe, to maybe a landscaper or whatever. And then you have a physical indication of where the water levels were. That's all I was trying to say. And then you can go and measure your Y values. You can do a visual indication of the bulge if you want to by lining up the stakes on the first and the last, and then look at the other stakes to see if they rise above or below. That's all I was trying to say. So anyway, thank you, Jose.
Thank you very much, George. Thank you very much, the man of God. And thank you very much, Rumpus, for your feedback at the end. I really appreciate everybody. I'm going to stop the broadcast, and then I will share the Hangout link on the YouTube chat. So if anybody want to join the conversation offline, you are free to do so. thank you guys, and hopefully I can figure out what was going down with my OBS today. I could not do the open panel, so but I really thank you very much, and I will be back tomorrow. Works OBS works or not, and check out Schrodinger's cat channel. I'm gonna be on a special edition show with him later, some kind of an interview, discussion, whatever is gonna go down. So check Schrodinger's cat, and I will be up there. I'm probably gonna mirror it or maybe multi-stream it on my channel. Thank you very much, guys. I'm gonna close this down. I'll see you later. Boom.